Welcome to Astronomy Daily. I'm your host, Anna. Today we're diving into some fascinating developments across our cosmic neighborhood that highlight just how dynamic and surprising our universe can be. We'll begin our journey at Jupiter, where NASA's Juno mission has been peering beneath the surface of both the gas giant and its volcanic moon Io. The spacecraft's instruments have revealed remarkable insights about Jupiter's massive polar cyclones and detected evidence of still warm magma flowing beneath Io's crust. Then we'll check in on NASA's Psyche mission, which is currently experiencing some unexpected issues with its electric propulsion system. Don't worry though, engineers are on the case and have redundancy built in for precisely these kinds of challenges. We'll also take a fascinating historical detour to explore how scientists throughout the centuries imagined alien life. You might be surprised to learn that many prominent thinkers once believed every planet, star, and even the vacuum of space itself must be teeming with living creatures. Speaking of surprises, astronomers have discovered something truly puzzling: a young family of over 1,000 stars that seem to be fleeing their birthplace in a tremendous hurry. This star cluster, nicknamed Ophion, is breaking all the rules about how stellar families typically behave. And finally, we'll explore an unexpected cosmic source of precious metals. It turns out that magnetars, incredibly powerful neutron stars with massive magnetic fields, may be responsible for creating up to 10% of the heavy elements like gold in our galaxy. So settle in as we explore these cosmic mysteries and cutting-edge discoveries that continue to reshape our understanding of the universe around us. Let's get started. NASA's Juno mission, launched in 2011 and orbiting Jupiter since 2016, continues to revolutionize our understanding of the solar system's largest planet and its moons. Originally planned as a 5-year mission, Juno has been extended and is now scheduled to continue operations until September of this year, or until the spacecraft itself can no longer function. One of Juno's most fascinating recent discoveries comes from its microwave radiometer, or MWR, an instrument initially designed to study Jupiter's clouds. Scientists cleverly repurposed this technology to examine Io, one of Jupiter's 4 Galilean moons, first observed by Galileo Galilei back in 1610. What they found was surprising: evidence of still warm magma flowing beneath Io's cooled surface crust. As Shannon Brown from NASA's Jet Propulsion Laboratory explains, when we incorporated the MWR data with JIRM's infrared imagery, we were surprised by what we saw. This cooling magma appears to be present at virtually every latitude and longitude they examined, with approximately 10% of the moon's surface showing these remnants. These findings help explain Io's extraordinary volcanic activity. The moon essentially functions like a car radiator, efficiently transferring heat from its interior to the surface where it can dissipate into space. It's a remarkable cooling system that helps regulate the moon's intense internal heat. Meanwhile, Juno has been conducting groundbreaking measurements of Jupiter's atmospheric temperatures since 2023. For the first time ever, scientists have been able to measure the temperature of Jupiter's north polar cap, discovering it's approximately 11 degrees Celsius cooler than surrounding areas. This polar region is also encircled by powerful winds exceeding 160 kilometers per hour. Perhaps most spectacular are Jupiter's polar cyclones, which Juno has been meticulously tracking. Unlike hurricanes on Earth, which form and move in isolation, Jupiter's cyclones operate quite differently. The gas giant hosts a massive northern polar cyclone with a diameter of 3,000 kilometers, nearly as large as Earth's moon, surrounded by 8 smaller cyclones, each still larger than the dwarf planet Pluto. As these cyclones drift toward Jupiter's pole, they interact with each other in fascinating ways. Juno co-investigator Yohai Caspi describes it as a mechanical system of springs, with the cyclones bouncing off one another while slowly drifting westward in a clockwise pattern around the pole. As Scott Bolton, Juno's mission principal investigator, puts it, everything about Jupiter is extreme. From its enormous polar cyclones to its fierce jet streams and the intense volcanic activity of Io, Jupiter's system continues to demonstrate the immense energies and complex dynamics at work in our solar system's most massive planet. Next up today, NASA is currently investigating a concerning issue with the electric propulsion system on its Psyche spacecraft, which is on a mission to the main belt asteroid of the same name. On April 1st, the electric thrusters abruptly shut down when pressure fell in a line feeding xenon propellant to the system. According to a statement released by NASA in late April, the pressure dropped from 36 pounds per square inch to 26 pounds per square inch, triggering the shutdown. This information wasn't widely publicized until April 30th, when more details began to emerge about the situation. The Psyche spacecraft launched in October 2023 and had just activated its Hall effect thrusters this past May. These thrusters, combined with a Mars gravity assist scheduled for May 2026, are crucial for the spacecraft to reach its destination asteroid by August 2029. Without properly functioning thrusters, the entire mission timeline could be jeopardized. Louise Proctor, director of NASA's Planetary Science Division, addressed the issue at a recent meeting, saying that teams at JPL are working diligently to identify the specific problem. Both the electric propulsion system and the spacecraft bus were provided by Maxar Space Systems, formerly known under a different name. Fortunately, NASA has stated that Psyche can continue to coast until mid-June before there would be any significant impact on its trajectory. Engineers are exploring potential solutions, including switching to a backup propellant line that was wisely incorporated into the spacecraft's design. As Proctor reassuringly noted, this kind of thing happens, and that's why we build redundancy into our missions. We don't have any concerns at the moment about it, but we're obviously keeping tabs on it. Prior to this issue, Psyche had been performing well since its launch on a Falcon Heavy rocket. However, the mission itself has faced challenges throughout its development, including software testing delays that pushed its launch back from August 2022 to October 2023 and increased the mission's cost from $1 billion to $1.2 billion. An investigation into these earlier problems revealed broader institutional issues at JPL, stemming from heavy workloads and communication problems within the laboratory. The current thruster issue appears to be unrelated to these previous challenges, but serves as another reminder of the inherent difficulties in deep space exploration. Okay, time now for a little history lesson. Long before we began searching for biosignatures on distant exoplanets, scientists and philosophers were convinced that intelligent life must exist throughout the cosmos. It's fascinating to look back at how certain many thinkers were that aliens not only existed, but populated virtually every surface in the universe. This conviction began taking shape in the early 1500s, when scholars like Nicolaus Cusanus argued that countless stars and planets must exist beyond our own. Remarkably, Cusanus even believed the sun itself was inhabited by what he called bright and enlightened intellectual denizens. He wasn't alone in this thinking. The Italian philosopher Giordano Bruno similarly reasoned in 1584 that it would be ill if the whole of space were not filled with life. These early speculators operated on a simple but compelling logic. Why would so much cosmic real estate exist if not to be occupied? The belief that everything in existence must serve a purpose led to the conclusion that uninhabited worlds would represent a cosmic waste. This thinking became remarkably mainstream over subsequent centuries. The conviction that every cosmic surface must host life led to some extraordinary claims. The English astronomer Edmund Halley suggested in 1692 that Earth itself must be hollow and filled with nested spheres to maximize living space. Others proposed that even the void of space itself teemed with microorganisms, with the French diplomat Benoit de Maillet theorizing in the 1720s that seeds of living creatures circulate throughout the cosmos. Perhaps most amusing to our modern sensibilities were the cosmic censuses conducted in the 1800s. Thomas Dick, a British theologian and astronomer, used England's population density to calculate that our solar system must house nearly 22 trillion inhabitants. He later expanded his estimate to the visible universe, arriving at the specific figure of 60 sextillion 573 quintillion living beings. Dick confidently declared that there is but one religion throughout the universe, conveniently, his own. As late as the 1890s, some scholars still maintained that the sun was inhabited. A German named Karl Goetze published a book in 1896 insisting that dinosaurs and mammoths roamed the sun's clement polar regions alongside humans. Even mainstream scientists like biochemist William Thierry Prayer speculated that suns might be glowing organisms whose breath may perhaps be shining vapor. This assumption of cosmic abundance finally began to crumble in the early 20th century. The discovery of radioactivity revealed that space is filled with harmful radiation, while advancing science clarified the stringent conditions required for life to exist. By 1926, English cosmologist James Jeans concluded that the physical conditions under which life is possible form only a tiny fraction of the range of physical conditions which prevail in the universe. Our modern, more cautious approach to extraterrestrial life represents a profound shift from centuries of wishful thinking. Perhaps this historical perspective should remind us to be equally careful with today's tantalizing biosignature discoveries. Next up, as you should know by now, I love a good mystery. In a cosmic puzzle that's leaving astronomers scratching their heads, over 1,000 stars are breaking up their family reunion far sooner than expected. This newly discovered star cluster, nicknamed Ophion after its home constellation Ophiuchus, is behaving in ways that defy our understanding of stellar families. Typically, stars born together from the same molecular cloud stay clustered for hundreds of millions of years before gradually drifting apart. The Pleiades cluster, visible to the naked eye in Taurus, is still tightly grouped after 100 million years. The more dispersed Beehive cluster in Cancer has been together for around 600 million years. But Ophion, located about 650 light-years away, is essentially a stellar family in the midst of a dramatic breakup, despite being just 20 million years old. As Dylan Hewson of Western Washington University, who led the discovery team, explained, Ophion is filled with stars that are set to rush out across the galaxy in a totally haphazard, uncoordinated way, which is far from what we'd expect for a family so big. What makes this cluster unique is its unusually high velocity dispersion. In normal star clusters, the difference between the fastest and slowest moving stars is just a few kilometers per second. In Ophion, that difference is a whopping 20 kilometers per second, meaning these stars are moving far too fast to stay together for long. The only reason we currently see these stars as a group is that they're so young they haven't had time to completely separate yet. We're essentially witnessing a stellar family portrait taken just before the children leave home forever. This discovery wasn't immediately obvious. Hewson and his colleague Marina Kunkel of the University of North Florida spotted Ophion while testing a new model called GaiaNet. This tool can simultaneously analyze the spectra of millions of stars using data from the European Space Agency's Juno Mission, which has measured the position, velocity, distance, and spectra of approximately 2 billion stars. So what caused this premature stellar scattering? Examining the Gaia data more closely, the team noticed several superbubbles, large voids created when supernova shockwaves blow away interstellar gas. It's possible that after Ophion's stars formed, much of the remaining gas was blown away by these stellar blast waves. Losing all this mass could have loosened the cluster's gravitational hold on its stars. Alternatively, gravitational tidal effects from neighboring star-forming regions might have given Ophion's stars an extra push. As Kunkel noted, without the huge, high-quality datasets from Gaia and the new models we can now use to dig into these, we may have been missing a big piece of the stellar puzzle. This discovery suggests there may be other young families of stars racing apart that we simply haven't recognized yet, challenging our understanding of how stellar nurseries function and evolve. And finally, today, have you ever wondered where the gold in your jewelry comes from? Most of us know it's mined from the Earth, but where did the Earth get it? The cosmic origins of heavy elements like gold have long fascinated astronomers, with supernovae and neutron star collisions typically given credit for forging these precious metals. Now, an unexpected cosmic goldsmith has entered the scene: magnetars. Magnetars are perhaps the most extreme objects in our universe. These rare neutron stars possess magnetic fields up to 1,000 trillion times stronger than Earth's. Formed from the collapsed cores of massive stars after supernovae, they're essentially the ultra-dense, city-sized remnants of stellar deaths with magnetic fields that boggle the mind. What makes this recent discovery so exciting is that these cosmic powerhouses may be responsible for creating up to 10% of all the heavy elements like gold and platinum in our galaxy. The breakthrough comes from Anirudh Patel, a doctoral student at Columbia University, who led a team analyzing 20-year-old archival data from NASA and ESA telescopes. Occasionally, magnetars undergo dramatic starquakes that release astonishing amounts of energy through giant flares. These flares, visible even from other galaxies, create the perfect extreme conditions for something called rapid neutron capture, essentially the fusion of neutrons into heavier atomic nuclei. This process is precisely what's needed to create elements like gold. The discovery solves a persistent cosmic mystery. Back in 2017, astronomers confirmed that collisions between two neutron stars could create gold and platinum. This was a major breakthrough, observed through both NASA telescopes and LIGO gravitational wave detectors. However, these mergers occurred too late in the universe's history to explain the earliest heavy elements we observe. That's where magnetars come in. As Eric Burns, a co-author of the study published in the Astrophysical Journal Letters, explains, this finding represents a breakthrough that solves a major cosmic mystery using nearly forgotten data. Since magnetars appeared early in the universe's history, they could have been responsible for creating the first gold. The research team initially predicted that heavy elements from magnetars would appear in visible and ultraviolet light, and possibly in gamma-ray signals too. After reviewing gamma-ray data from 2004, captured by NASA's RESI and WIN satellites, they found an unexplained signal that matched their prediction-likely evidence of heavy element creation during magnetar giant flares. Looking ahead, NASA's upcoming Compton Spectrometer and Imager mission, launching in 2027, will study high-energy cosmic events, including magnetar flares, in greater detail. As a wide-field gamma-ray telescope, SOSI will be able to identify individual elements created in these powerful events, advancing our understanding of their cosmic origins. So the next time you admire a gold ring or necklace, remember that you're wearing the products of some of the most violent and extreme events in our universe, including, perhaps, the cataclysmic flares of magnetars that occurred billions of years before our solar system even formed. What an incredible journey we've taken through our cosmic neighborhood today. From Jupiter's swirling storms to stars fleeing their birth clusters, and from historical perspectives on alien life to the violent magnetar flares forging gold, our universe continues to reveal its secrets in the most unexpected ways. These discoveries remind us of how interconnected cosmic phenomena truly are. Jupiter's cyclones and Io's cooling magma teach us about planetary evolution. The Psyche mission's thruster troubles highlight the challenges of space exploration even as we reach farther into the cosmos. Our changing views on extraterrestrial life demonstrate how science evolves with new evidence, while the mystery of Ophion's dispersing stars shows there's still so much we don't understand about stellar life cycles. And perhaps most poetically, learning that the gold we cherish comes from the most violent cosmic events connects us directly to the stars in a tangible way. The atoms in our jewelry, our electronics, and even our bodies have journeyed across space and time to be here. This has been Astronomy Daily with me, Anna. If you've enjoyed today's cosmic tour, I invite you to visit our website at astronomydaily.io, where you can sign up for our free daily newsletter and catch all our previous episodes. You can also subscribe to Astronomy Daily on Apple Podcasts, Spotify, YouTube, iHeartRadio, or wherever you get your podcasts from. That way, you'll never miss our regular explorations of the universe and all its wonders. Until next time, keep looking up. The cosmos awaits with countless more stories to tell.